In this video, we are going to be extending our knowledge of the Pythagorean theorem. In this case, we are going to talk about how we can use the Pythagorean theorem in the coordinate plane and how we can use it to determine the distance between any two points. So just to review the Pythagorean theorem, it states that if a triangle is a right triangle, then a squared plus b squared is equal to c squared. And just to remind us all of the variables and what they mean, a and b are the legs of a right triangle, and c is the hypotenuse of that triangle. And again, a and b are the legs of a right triangle. So you can see in the diagram here, A and B are the legs. They are directly next to the right angle. C is the hypotenuse. It's the longest side, and it is across from the right angle. It's also the longest side of our triangle. We can use the Pythagorean theorem to find any missing side in a right triangle if we are given two sides. So for example, here's our right triangle, and let's say we have a side of 3 and a side of 4 and an unknown side x. So in the theorem, leg squared plus another leg squared is equal to the hypotenuse squared. And in this right triangle, x represents the hypotenuse. So let's fill in the information that we know. 3 is a leg. Let's replace A with 3. 4 is also a leg. Let's replace B with 4. And the hypotenuse is x. Let's replace C with x. So now we need to solve the equation for x to find the length of the hypotenuse of this right triangle. First thing we need to deal with is the exponents. Anytime you see in superscript 3 squared, this just means 3 times itself, or the base number 3 multiplied 2 times. 2 3's multiplied together. Same thing with 4 squared. This is just 4 times 4. So we need to evaluate these exponents. 3 squared is 9. 4 squared is 16. And x squared stays the same. The goal is to solve for x. So from here, we need to add the terms on the left side of our equation. 9 plus 16 is 25. And that's equal to x squared. To get x by itself, the opposite or inverse of squaring a number, because x is a number, the inverse of squaring a number is taking the square root. We need to take the square root of both sides of the equation. So the square root of x squared is x, and the square root of 25. And as a reminder, this is not dividing 25 by 2. This is saying what number times itself is equal to 25. And so we need to remember in a right triangle or in any geometric figure that we don't want negative side lengths. I know that -5 times itself is equal to positive 25, but I know that the hypotenuse can't be a negative number. There are no negative distances. So we want the positive square root. The positive square root of 25 is 5. 5 times itself is 25. So the hypotenuse of this right triangle, x, is 5. So let's try this out in the coordinate plane. We are going to approximate the length of the hypotenuse in this diagram to the nearest tenth using a calculator. This is a great reminder to you if you have not been using a calculator yet. Now is the perfect time to start. Okay, so I already see my right triangle. I can identify the right angle. It's up in the top right corner. And just for clarity's sake, I'm going to label all of the points that I see. So this point is -3, +2. And I'm seeing 2, 2. And my last point is 2, -2. And you'll see why I'm labeling these coordinates in just a second. We need to find all of the dimensions we know in this diagram. I want to calculate how long this distance is. So my x value is -3. And my x value across this segment is +2. If I were to calculate the distance from left to right by just counting, I would get 1, 2, 3, 4, 5. 5 is my length. However, I can also find this distance by subtracting the x values from each other. So if I subtract -3 from 2, so 2 minus -3, that would give me the same answer. The distance is still 5. Now the vertical leg that I'm seeing in the diagram, I'm going to find the distance in the y values. So if I were to count normally from top to bottom, I would get 1, 2, 3, 4. The side length would be 4. Or I could calculate by subtracting the y values from each other. So this would be 2 minus -2. 2 minus -2 is just 2 plus 2, which is 4. And now we have our unknown side. The unknown side is diagonal. There's not really any way for me to count. There are no units that I can count here. So that's why we're going to use the Pythagorean theorem to find out what the hypotenuse is. I know this is the hypotenuse because it's across from the right angle. So let's rewrite the Pythagorean theorem here. I know that that is a squared plus b squared equals c squared. So let's call the horizontal leg of the triangle A. So 5 squared. And then the vertical side of the triangle is 4 units, so that's 4 squared. And we don't know the hypotenuse, so that is just c squared. And from here we can solve the Pythagorean theorem as normal. So we need to evaluate our exponents first. 5 squared is 25. 4 squared is 16, and it's equal to c squared. Combining our terms on the left side of the equation, 25 plus 16 is 41. And that's equal to c squared again. We're going to take the square root of both sides to get c by itself. And c is going to be the square root of 41. 41 is not a perfect square. There are no two integers when you multiply them. There is no integer when you multiply it by itself that equals 41 exactly. So we're going to have to estimate c. And when I plug this into my calculator, c is approximately 6.4 units. So now we're going to work with something called the distance formula. And there is a way to manipulate the Pythagorean theorem. There's a way to change it around algebraically so that we can find the distance between any 2 points without an image. So over on the right side of my picture, I have 2 points. Let's call the first one x1, y1, and that can represent any values for x and y. My second point is x2, y2. That represents, again, any values of x and y. And the distance between those points in a straight line is d. So I can create a right triangle. And I'll demonstrate here. I'm going to create a right triangle by extending the horizontal and vertical distances between those 2 points. So the green line represents my vertical distance, and the blue line is going to represent the horizontal distance. And of course, they meet they meet in a right angle. So D would represent the distance between the 2 points, and it's also the hypotenuse of this right triangle. Let's call the blue segment A and the green segment B. So now we can use the Pythagorean theorem to solve for D. Normally we would use C for the hypotenuse, but D works too, D for distance. So you might be thinking, well, there are no values, so I can't really determine the length of the blue side and the green side. Well, yes, you can. We can actually say that we can find the distance horizontally by subtracting the x values. The second point in the top right has an x value of x2. The point in the bottom left has an x value of x1. We can label this as x2 minus x1 units. You take the x values and you subtract them to find the difference. And B, same thing, except we are going to find the vertical distance. We are going to find the change in the y values. So this would be y2 minus y1. So let's update our Pythagorean theorem. And again, A represents our horizontal distance. This could be any length. And B represents the vertical distance. And this may make more sense once we put some actual numbers to this, but I wanted to show you algebraically how do we get to this distance formula I'm going to show you. Okay, so going back to the Pythagorean theorem, a squared plus b squared equals d squared. Now I have some values for a and b. I know that a is x2 minus x1. And I'm squaring that value. And B is my vertical distance. And we labeled that as y2 minus y1. And we're going to square that value as well. And that's all equal to d squared, the distance squared, my hypotenuse squared. And so to get d by itself, to find the actual distance, remember we need to take the square root of both sides. So the square root of all of this, the square root of x2 minus x1 squared plus y2 minus y1 squared is equal to d. This right here is the distance formula. This is the formula we can use to find the distance between any 2 points on the coordinate plane. Could we still use the Pythagorean theorem? Yes, it's the exact same thing as the distance formula. All I did was change around some numbers, assign a few values. They are the same formula through and through. Okay, so now we're going to take that same problem as before. And we are going to use the distance formula, and I will show you we are going to end up with the same answer. Just as a refresher, we said that C was approximately, let me go back here, C was approximately 6.4 units. So let's keep that answer in the back of our mind while we're working. So we are going to use the distance formula to find the third side. Okay, so like I said before, it's very useful to label your points. So I know that this point here is -3, 2. This point is 2, 2. And my third point is 2, -2. And we are missing the hypotenuse. Again, if this is our right triangle, this is our missing side, C. We can label this as D for distance, but we need to find the distance between this point here and this point here. So my two coordinates that I'm going to be using, my points are -3, 2, and 2, -2. Here's the cool part about the distance formula. You don't actually have to find the side lengths, the other side lengths of this triangle. You can just use the coordinates and find the distance without doing that extra work. So the distance between those points, let's draw a big old radical symbol here. And for clarity's sake, I want to assign variables to these points. My first coordinate is -3, 2. Let's call this x1, y1. 2, -2. Let's call that x2, y2. That way we can substitute these into the distance formula a little bit easier. It makes it visually easier to do. Let me change my pen color here. So the first part says x2 minus x1 squared. So x2 is 2 minus x1. x1 is -3. So 2 minus -3 squared plus, and then I'm looking back up the formula again, y2 minus y1 squared. I know that y2 is -2 minus y1. And I'm looking at y1, it is +2. So -2 minus 2 squared. So now we need to use a little bit of PEMDAS or GEMMA. I need to work with my parentheses first. If I have some operations to do in parentheses, those come first. So 2 minus -3 is going to be +5. This is 2 plus 3. So 5 squared plus, and then -2 minus 2 is -4 squared. Now I'm going to evaluate my exponents. 5 squared is 25 plus -4 squared. -4 times -4 is +16. Remember that a negative times a negative is a positive. So D is equal to, and then I'm going to add the terms inside the radical, the square root symbol. So D is going to equal the square root of 41. And when I estimate the square root of 41 on my calculator, D is approximately 6.4 units. So as you can see, we arrived at the same answer as before. All the distance formula is taking the Pythagorean theorem and combining it so that we're only really using order of operations now. We just have to substitute the values we know, taking the coordinates we know, plugging them in, and then using order of operations, finding the square root, and then we're done. So let's try out an example, finding the distance between 2 points. And again, you can use the Pythagorean theorem or the distance formula. The choice is yours. I'm going to be modeling the distance formula because it's a new concept to us. So, without further ado, Francesca wants to find the distance between her house on one side of a lake and the beach on the other side. She marks off a third point forming a right triangle as shown. The distances in the diagram are measured in meters. So we want to find the distance between the house and the beach. So let's do a little labeling here. I know this is my right angle, and I know this is the distance I need to find. The dotted line is my distance from the house to the beach. And I have my coordinates already. So my points that I am using for sure are the house points, which is 10, 20, and the beach points, 280, 164. And just for the sake of visual aids here, I'm going to label the house coordinates as x1, y1. This is my first coordinate. And the beach coordinates as x2, y2. So that I can see exactly where I'm going with the distance formula as I'm making my calculations. So we have the distance formula posted here. Let's plug in what we know. So D equals, and a big radical symbol, x2 minus x1 squared. x2 is 280 minus x1, which is 10, and we're going to square that, plus y2 minus y1 squared. y2 is 164 minus y1, which is 20, and that is squared. From here, we are doing the operations we see in the parentheses first. 280 minus 10 is 270, and that's squared, plus 164 minus 20 squared. So 164 minus 20 is 144, and we are squaring that. From here, we are evaluating our exponents. So we're going to have some big numbers here. 270 squared is 72,900 plus 144 squared, which is 20,736. I told you we were going to be working with some big numbers today. So D is equal to the square root of 93,636. And when we estimate that value, actually we don't need to estimate. The square root of 93,636 is exactly 306 meters. So it is 306 meters from her house to the beach. All right, we've got a multi-step problem here. The locations of 3 ships are represented on a coordinate grid by the following points. P is at -2, 5, and I'm going to plot these as I go. P is at -2, 5. Q is at -7, -5. and r is at 2, -3. Okay, and we are asked which of the ships are farthest apart. Is it the distance from P to R, P to Q, or Q to R? And so we are definitely going to need to use either the Pythagorean theorem or the distance formula to solve this problem. Like I said, either method is valid. We're going to use the distance formula today. I just wanted to show you a visual of what these points look like and how it's not exactly clear which distance is the farthest. So we're going to do this on the next page. I don't even need the graph to complete the distance formula. I just need those coordinates. So just to prove my point, I am going to separate my page into 3 parts. Now I'm going to use these 3 parts to determine which of the lengths is farthest. So the first distance I am going to find is the distance from P to Q. And then next I will find the distance from Q to R. And lastly, I am going to find the distance from P to R. From P to R. So we're going to use the distance formula 3 separate times. Again, for visual clarity, I know that P is -2, 5, and Q is -7, -5 for my first distance calculation here. And I'm going to assign the coordinate P as x1, y1, and Q is going to be x2, y2. So the distance is going to be equal to the square root of x2 minus x1 squared. So x2 is -7 minus x1, which is -2, square that, plus y2 minus y1, so -5 minus 5 squared. And again, using order of operations. Parentheses first. -7 minus -2 is just the same as -7 plus 2. That's a -5 squared. Plus -5 minus 5 is -10. And we're squaring that as well. So for D, distance is equal to, now we're going to evaluate our exponents. -5 times itself will be +25. Plus -10 times itself is +100. So adding those terms together, D is equal to the square root of 125, which is approximately, to the nearest tenth, let's say, it's approximately 11.2 units. But we're not done. We also need to compare this distance to the distance from Q to R and P to R. So Q is at -7, -5, and R is at 2, -3. And again, assigning variables here, labeling my points. Q is going to be x1, y1. R will be x2, y2. And let's do the distance formula again. Distance is equal to the square root of x2 minus x1 squared, so 2 minus -7 squared. If you have a negative value and you are subtracting it, don't forget the negative. 2 minus negative 7 plus y2 minus y1 squared. Negative 3 minus negative 5 squared. So D is equal to, so 2 minus negative 7 is just the same as 2 plus 7, so that's 9 squared, plus negative 3 minus negative 5, or negative 3 plus 5, is positive 2 squared. So distance equals the square root of 81 plus 4, which means it is the square root of 85. And when I estimate the square root of 85 to the nearest tenth, I get D is approximately 9.2 units. So then I know that the distance from Q to R is not the farthest apart. It's not the greatest distance. So we've got one more shot. Let's see if P to R is a greater distance apart than P to Q. So P is negative 2, positive 5, and R is 2, negative 3. Labeling my points, P is going to be x1, y1, and R is going to be x2, y2. You don't need to label the points x1, y1, x2, y2 every single time, but I'm a very visual person. I like to have labels so that I don't make mistakes. There are a lot of values that we're substituting in the distance formula. It's nice to keep everything on track. So our last round of distance formula here. D equals the square root of x2 minus x1 squared. x2 is positive 2. Oops, no comma. We're subtracting here. So 2 minus negative 2. x1 is negative 2. 2 minus negative 2 squared plus y2 minus y1 squared. y2 is negative 3. And we are subtracting 5 from it, and that is also squared. And like before, parentheses come first. 2 minus negative 2 is 2 plus 2, so this is 4 squared, plus negative 3 minus 5 is negative 8 squared. Evaluating our exponents, 4 squared is 16, and negative 8 squared is negative 8 times negative 8, which is positive 64. So D is equal to the square root of 80. And by now you're probably seeing exactly which distance is farthest apart. The square root of 80 is approximately 8.9 units. So in comparing all of these distances to each other, in green we have from P to Q, in yellow is the distance from Q to R, and in blue is the distance from P to R. So I know that based on these values here, I know that the distance from P to Q is the greatest. So PQ is farthest apart. And that was the end of our presentation. So we can use the distance formula and the Pythagorean theorem to find the distance between any 2 points. And again, the distance formula with points x1, y1, and x2, y2 is the square root of x2 minus x1 squared plus y2 minus y1 squared. Thank you for watching and have a great day.